Good morning to Dr. Francisco and good afternoon to all my friends from India. So I, Rohan Katti, on behalf of SRM OSA Student Chapter and SRM Institute of Science and Technology, welcome Dr. Francisco to this guest lecture, and I also welcome all the attendees who have joined us in this lecture virtually. So before we begin the lecture, I would like to introduce you all to today's speaker. Dr. Francisco has received his BSc degree in Information Engineering from University Degel Studi di Padova, Italy in 2008, and he then received dual MSc degree from the same university and Technical University of Denmark in 2011. He then received his PhD degree from Technical University of Denmark in 2014, and during his PhD period, he spent 7 months at Fraunhofer Institute of Telecommunications, Germany, and then he worked as a postdoc researcher at the Department of Photonics Engineering within the Center of Silicon Photonics for Optical Communications, where he worked on all optical signal processing, nonlinearity compensation techniques. And his research interests are very diverse, ranging from the field of nonlinear optics, integrated optics, silicon photonics to optical transmission systems, optical signal regeneration, digital signal processing, and machine learning for photonic systems. And while his PhD, he also spent a month working at the prestigious Aston Institute of Photonic Technologies. And then he's currently involved with European Research Council's Consolidator Grant, FreeCom, under Associate Professor Zieber, where he works on inverse scattering transform and machine learning techniques applied to coherent communications. And he's actively involved in 4 research projects. He has co-authored more than 100 journal and conference papers, and he's a Optical Society of America Young Professional Volunteer member, an IEEE Young Professional member, and he is serving as the technical subcommittee member for the Conference on Lasers and Electro-Optics since 2018. So we welcome you, sir, once again, and I invite you to deliver today's lecture on advancing photonic systems through machine learning.
Thank you very much for the very kind introduction, and especially for this nice invitation. Look forward to discussing some of the topics that we are well, very interested on, and that we have worked quite a bit over the last few years on with you, and get some feedback and maybe some even potential collaboration there. So basically what I will be discussing today is a little bit our approach on using machine learning techniques for photonic systems in general. So I've recently joined a new group called Machine Learning and Photonics Systems. And so that's where we really put our focus, as the name says. But before getting straight to that, just a little bit of background of where I come from. So I work at the Technical University of Denmark, so DTU, which I've just to be clear, that's not Delhi Technical University. I've discovered a few years back that there's a very common acronym. But basically, we are based in Denmark, which is that tiny land over there. And our institute is just like north of Copenhagen, so the capital. And we have a fairly diverse focus on several aspects of photonics. So from photovoltaics to biophotonics to communication and devices fabrication. But in particular, the group I'm part of is called Machine Learning and Photonics Systems, as I mentioned. So we're a few senior members, so under the lead of Associate Professor Da Ros, with a few postdocs and mainly PhD students working on a number of topics related to photonic systems. So also with a fairly diverse sort of background and nationalities amongst us. And we currently have also an open PhD position if somebody is looking for something to do next. In terms of topics, well, as I mentioned, we sort of cover a broad range of applications of machine learning and maybe signal processing as a more general sort of definition applied to photonic systems. So both for more fundamental optics, say for characterization of devices, especially lasers and frequency comb or fiber sensing or even some quantum activities. So I'll touch briefly on the device characterization and the quantum activities towards the end of this talk. But we also historically have a close link on optical communication systems. So looking at basically increasing the capacity of fiber optics systems and increase the throughput and develop advanced signal processing techniques. So after this brief introduction, what I would like to cover within this talk are more or less the following points. And I'll be also happy to take questions at any time if somebody wants to jump in, or we can take them at the end, whatever works best. But basically, the first part will be a very brief introduction of machine learning and some of the techniques that we have been mainly focusing on. And then I'll move on into more, optics and photonics applications of it. So looking at two specific techniques, so applying system learning or Bayesian filtering. And for each one of them, I'll mention a couple of applications where we have put quite some effort into, applying them to solve problems for the for photonic systems and optics in general, and then conclude a little bit the talk. But starting with the introduction on machine learning, well, if just to set a little bit the scene, what is really machine learning? Well, if you ask Google right now, you get a lot of different answers. But if we go a little bit back to a little bit over 60 years ago, then someone defined it as the field of study that gives computers the ability to learn without being explicitly programmed. This is a little bit of a broad definition. So in the 1998, Mitchell then came up with a bit more mathematically rigorous sort of framework to explain what machine learning is in his point of view. And he basically defined that the computer program is said to learn from an experience. So you need to have some experience, some data that you are providing to a computer program, and with respect to some task. So it's a specific problem that you're trying to solve, and some performance measure P. So you are defining a metric where you're saying that how the performance, so this on this task is improved as measured with this metric, and that gets improved by the computer program learning from the initial experience of the data that we are providing it with. So there's two key points to take from this, is that from the very beginning, machine learning was defined as a way to learn from data, and more importantly, it's also learning from data or experience, but with the goal to improving the performance in performing a specific task. Now, where do we use machine learning currently? Well, machine learning is pretty much affecting any aspect of our lives. So from pattern and image recognition, self-driving car, cyber fraud detection, or what we use every day by just going to check our emails, so spam filtering, as well as more critical functions in helping medical diagnosis, or figuring out what TV series or a song we want to watch or listen to next, which is lately almost equally critical. Now, again, there's a lot of places where we can apply machine learning, and if we go back at doing a search on Google, well, there's a lot of things that pop up, from neural networks to different frameworks to very impressive results being achieved lately. So instead of drawing a little bit, I just want to maybe go a little bit back to the beginning and discuss things by looking at a specific example. So if we go back to the definition from Mitchell in 1998, with the three key concepts of learning from an experience with respect to a task, to improve a certain performance metric. And we look at one of the actually very first applications of machine learning, which has been handwritten digit recognition. So this was actually applied by the US post system way back, where they used this automatic handwritten digit recognition to basically read postcodes from mails, from letters, to decide where to route them. So if we consider this specific problem and we try to figure out what task experience and performance are with respect to that, well, the task is, of course, that we want to correctly recognize the handwritten digits. And in order to do that, well, a computer program needs first to be taught what the correct answer is. So that means that we need to provide it with experience, or with data, which in the specific is the manually recognized digits. So a human will be able to tell that this is a 3, this is a 4, this is a 2, this is a 1, and we need to teach the computer or program to learn that. And our performance metric then that tells us how successful we've been at that is then the percentage of digits that have been correctly recognized. So of course, the moment we have experience that we need to feed into a computer program, well, that sort of automatically leads to the fact that we are doing some training of the program such that it can start learning how to solve the problem or the task. So this means we need to build up a training set, which in the specific cases is composed by the set of handwritten digits plus the associated labels. So we have a set of input and target vectors, where the input vectors are the actual images, so in the specific 28 by 28 pixel digits, so which are handwritten by several people. And you can actually find these data sets containing thousands of different ways of handwriting specific digits available, and that's actually a very standard data set that can be used to benchmark machine learning algorithms, and it's used, say, even in competition, to basically benchmark different algorithms, figure out which ones are the most effective, both in terms of the performance exactly that they provide, but also in terms of training time and so on. So, but together with the data set of pictures, we also need the labels. So we need to tell the program that this picture explicitly corresponds to a 3. So generalizing the whole approach, this is what is normally done for machine learning. So we are training a model where we have some inputs and some targets. And in the training phase or learning phase for the model, these targets are given. And then what we do is we tune the parameter of the model such that when we input a 3, then the output of the model matches our target, which is the number 3. That is the first step. However, that will only will not really lead to our final outcome, because of course we can fine tweak the models such that it's very good at detecting this specific picture. I mean, once it has seen it once and has been told that that's a 3, well, then we want it to actually be able to generalize, to take another picture, which is a completely different way of writing the number 3, and still be able to correctly predict that that is indeed the same number. Now, generalization is defined as the ability to correctly characterize examples that are new, so that they have not been seen in the training phase, and that's the way then we can really be sure that our model is effective in solving a problem. So then as I sort of gave you already maybe a hint, that there's 3 key components to machine learning. There's the data, so the experience that we use to train our model. This data is actually chopped up into features, so which are the important parameters and variable within the data, and those can be both known in advance or they might need to be extracted. We might not really know if we have a very complex system which we are trying to model. We might not clearly know have like the level of importance of the different inputs with respect to giving a certain output. There might be some parameters that are particularly relevant, while others might not be that much. And this is something that machine learning can also help us identify. And finally, there's the more classical computing part, which is the algorithm. So the specific method that we try to apply and that we train to solve a given problem or a given task. Now, with respect to machine learning algorithms, there's three key categories that are usually considered. So the first one is the one that I've basically been discussing so far, which is called supervised learning. So this corresponds to actively teaching a computer program to learn how to perform a task. And so this corresponds to, if we have some data X and some associated output Y, to learn the mapping from X to Y. So either from the point of view of direct function or a statistical description, for example, P of Y given X. Now, within this big category of approaches, there's two subcategories that are particularly important. One is regression, the other one is classification. So in regression, what we are really doing is trying to learn the overall function describing our data. So you could think of a very simple example of regression as the case where we say want to predict the price of houses as a function of their size. And what we would try to do is normally some polynomial fitting through it, such that we then get a bit of a feeling of what the underlying relation is. Alternatively, classification is instead more focused on the marking classes of possible outputs. So we normally have only a discrete number of possible outputs, and a very clear example of classification relying on supervised learning is spam filtering. So the spam filter will not really need to learn a function, but we'll just need to learn whether an email should be marked as spam or not. So these are the approaches, the two main approaches which rely on us actively teaching the machine learning model how to perform a task. However, as I mentioned, sometimes we might not really have a clear picture of what the features that the machine learning model needs are. So in this case, instead of predicting an outcome as for supervised learning, we can do unsupervised learning. So in this case, what we really aim at learning is not really the output to the problem, so y equals to f of x, but rather trying to more understand the properties of the data that we have, and try to basically separate them into maybe groups or classes. So, and these are actually the two key subcategories of unsupervised learning. So one is clustering, the other one is density estimation. So in clustering, we group our data into separate classes. The other one gives us an idea of the statistics behind data. So just without really having further understanding of it. So pretty much describing the data. Finally, there's reinforcement learning, which is a more complex and rather more advanced approach, where what we really want to achieve is that through some feedback and positive reinforcement to the system, well, the machine learning model actually feedbacks on itself and improves its performances. So this is something that has been used a lot, for example, at the very beginning for teaching a machine learning model how to play chess, and has been fundamental in the achievement of Google a few years ago in implementing a machine learning framework that could go and beat actual human masters at that. So overall, to improve a program that is targeted at solving a specific task. Now, after this very general introduction, I would maybe want to move into a more, say, familiar territory, at least for me, which is how, where we can apply these tools to photonics and optics. And as I mentioned, I'll consider two specific approaches. So one is system learning, and the other one is Bayesian filtering. So if we start with system learning, well, that has actually led to a strong interest in the photonics community, with a lot of workshops and sessions at several of the major conferences, as well as to the point where NIST, so the National Institute for Standards in the US, has actually started last year an initiative to try to standardize some sort of data sets to be used for machine learning applications in optical communication. And if you're interested in learning more, at least in our group's perspective on this, we had I guess half a year back at this point, a sort of review article on optics and photonics, discussing some of the sort of forward-looking approaches, or the fields where we can see that intelligence and machine learning in particular can benefit photonics. So getting more to system learning itself, well, the idea is to learn a system. So we have a black box here represented by this unknown function. We can either learn direct mapping, so function from X to Y, so from our input to our output, but we might also want to learn, and I'll get back to this in a few slides, the inverse mapping actually. So how, what kind of input do I need to give my system to have a certain target, a certain output? So I want to learn the inverse of my actual system, such that that will tell me what input I need to give it to get a certain target. And similarly, we can also have a more probabilistic or statistical approach to it, which is sort of learning decision rules. And overall, a very effective way to do the system learning, so to learn either the direct or inverse mapping, is to use neural networks. Now, a framework that we have been developing quite a bit over the last couple of years has been to really do that. So to use neural networks to learn direct and inverse mappings. So where, again, the direct mapping, we take the input, we feed it to the neural network, and the neural network will predict our output since it has been trained to learn this direct function. While for the inverse mapping, we do the opposite. So if we have our complex photonic system and we want to know what input we need to give to get a certain output, then we want a neural network that, given a certain target output, can predict what the input to the system should be. So again, the inverse mapping. Now the question is, why would we want to use neural networks to do that? Well, there are a number of reasons. So sometimes the physical system has an accurate representation already. So we have the equations, we have the analytical models that can be solved numerically. But if we consider a lot of photonic systems, some of those models are particularly difficult and challenging to numerically compute with, say, nonlinear partial differential equations and so on. So it's particularly difficult to apply that model efficiently. Similarly, sometimes the physical system is actually too complex to have an accurate representation. We might have approximate model, but those might not be good enough for, depending on the application. On top of that, we can also train the neural networks directly from experimental data. This means that we can also capture some of the experimental challenges that maybe are particularly difficult to really model accurately again. And finally, we have the strong benefit that neural networks are really matrix multiplication and nonlinear functions, which are normally very much differentiable. This means that if we need to optimize with a certain target a system based on a neural network, well, we know how to calculate a maxima and minima if we have a differentiable function, which is pretty much just taking the gradient through them. Now, of course, as a disclaimer, does it always make sense to use neural network model? No, not really. If your problem is particularly simple, then applying a neural network is not really the solution. But again, when either the model is difficult to compute effectively, or we don't actually have an accurate enough model, that might make a lot of sense. So these are two cases that I will be discussing. So on the one side, the limitation of the model efficiency. So we have been using neural networks to model Raman amplifiers. On the other hand, for systems where we don't have a very accurate presentation, so autoencoders for optical communication systems. So with regard to the Raman amplifier, just a bit of a background for somebody who might not be too familiar with Raman amplifiers or Raman scattering. So Raman scattering is an effect that happens in optical fibers where you have transfer of energy at different frequencies through the interaction with the vibrational modes in the silica molecule. And when I think of Raman, is that it has a gain spectrum that covers roughly 40 terahertz at different levels of efficiency. And then it can be used very effectively for signal amplification in optical communication. So if we look at the, say, low loss spectral window of optical fibers, well, we have a number of communication bands, mainly the C and L band are used currently. But if we look at amplification technologies where we have doped fiber amplifiers that can cover some narrow bands in different combinations, where semiconductor optical amplifier, parametric optical amplifier, which are a little bit more broadband generally than fiber doped amplifiers, but are still not covering the full extent of the low loss window of optical fibers. Where Raman amplifiers, since they are basically can be positioned pretty much at any frequency, given that we have appropriate pumping wavelengths, then we can pretty much cover the whole frequency window of interest. Now, how do Raman amplifiers work? Well, if we have a target, say, gain profile versus frequency that we want to achieve, well, what we would normally want is start pumping our fiber with a certain frequency and a certain power. And what you can see over here is the gain spectrum due to the Raman effect. You see that one pump is not quite sufficient to get us there. But the moment we start increasing the number of pumps and optimize their frequency allocation and their power, then we start getting closer to that. And this is very much modeled by this system of partial differential equations, which is a nonlinear system. And so we sort of know how to do this. And we could optimize this by changing our pumps until we get to roughly our target. However, this is an iterative process, which is quite time consuming. And when we need to change our target, for example, then what happens is that we need to start again. We might not need to start again from scratch, but we still need to reiterate several times. And a Raman solver solving this set of equations is no simple task. So there's generally a long convergence time and the need for restarting the optimization for a new gain profile. So even if we use effective methods such as evolutionary algorithms, that is somewhat challenging. So where does ML help? Well, what we have just discussed, well, we have a system where you have some inputs, say the pump laser configuration, so wavelengths and powers, and at the output we have a Raman gain spectrum. So what we can do is we can apply what we discussed, so modeling both the direct and the inverse mapping through neural networks, or where the direct is from the pumps to the gains, and the inverse is from the gain to the pumps. What we really want to do, especially from the point of view of designing an amplifier, is the inverse mapping. So we want a certain target gain spectrum, and we want to know what pump lasers do I need to buy and what pump power do they need to run at. And the nice thing, again, with neural networks is that we can build this whole model out of experimental data. So if we have our experimental setup with the Raman amplifiers with a certain number of pumps, then we can just uniformly sample pump wavelengths and power and record some gain spectra. Now the set of pump powers and measured gain will be our data set that we can use for both training and validation or testing of our model. Additionally, what we have been quite extensively working on improving the prediction of just the inverse model, so from gain to pump configuration, has been to build up both the inverse and direct mapping. And once we have both neural networks, which are very well trained and lead to low error, we can use them in a sequential and iterative way where we refine the prediction from our inverse mapping by applying the direct model of our Raman amplifier and correct the predicted pump configuration by looking at the error between the gain predicted by our direct mapping using the pumps that our inverse mapping provides, and what was our initial target. And now this is back at telling you to go for an iterative approach. However, compared to the say genetic algorithm with the Raman solver, now we the inverse mapping already provides us a very good starting point for the iterative optimization. We have actually seen that in some cases this fine optimization does not provide further gain. We have already all the gain from the inverse mapping. And two, the neural network models are differentiable, so we can easily take the gradient descent through them. Now, how does that really look like? Well, we need to still, once we have trained all the models offline and do some prediction, even with the fine optimization, well, we need to get the pump configurations and consider a number of scenarios, generate what pumps we need, plug them back into the lab for experimental validation, and compare them with what were our targets. And what we see over here is that generally we get very good agreement with what we wanted. So the measure design gain is very close to our target, even over a very broad bandwidth. So we went all the way up to 15 terahertz of Raman gain. And with the fluctuations and the error that you see is basically mainly limited by the equipment that we had available. Now, I've discussed this for Raman amplifiers, but this is actually a very general framework that can be applicable to several photonics problems. So in general, well, you want to get the inverse and forward or direct mapping, and then you can use them sequentially to perform a final fine optimization. And this has been used, for example, in other applications by other group. So one example has been the design of photonics component and other kind of amplifiers. Is the connection still okay? Because things are a little bit slow on my side. I hope. Okay, good. Otherwise, please let me know.
Yeah, sure.
So as I mentioned, for photonics components, as well as more complex, say, meta surfaces and advanced structure design. So from the point of view of still applying the system learning, right now we are just trying to model a single system. So either direct or inverse mapping. Another thing that we have been looking at is a bit of a different problem, which is more related to optical communication itself. And it's learning how to best communicate over an optical fiber. When I mean best, I mean with the best performance or the maximum throughput or speed of the transmission that we can achieve. That can actually be done by having two neural networks or neural network-like models acting as encoders and decoders. So effectively as transmitter and receiver. And where the encoder has the goal of basically generate some signal which is robust to the channel impairment, while the decoder has the goal to basically re-extract the signal from the received data with high fidelity. And this is a very different problem in a way compared to the Raman amplifier, because this is a case where we don't really have an alternative way to do things, or we don't really know what are the optimum encoder and decoder. So what we have been looking at is training this autoencoder on an accurate model of the optical fibers, which basically relies on iteratively generating some symbols, applying our neural network transmitter, propagating them through the optical fiber, detect them with the receiver neural network, and then calculate some, again, performance metrics. This is one of the key points for machine learning. And then we can see how that performance metric, basically how the performance metric evolves as a function of the weights in our neural networks, and use that to iterate for the optimization. And we can do that actually with a fairly complex channel. So described by the nonlinear Schrödinger equation, for example, which is then again a case where we can apply this whole approach to systems that are particularly complex and of unknown solution. And there has been quite some work on this, both from our group and another group at the University College London, for both direct detection communication and coherent communication. We are mainly focusing on coherent. And we can see that we can get quite some nice improvements by using this approach. So this is what I wanted to briefly discuss in terms of system learning. Now I'll quickly touch onto a different technique that we have been applying systematically for, say, more physical system, which is the characterization of optical components, specifically lasers and frequency, and how that can actually help in the perspective of very low power quantum level communication. So for example, for quantum key distribution applications. So this relies on the concept of Bayesian filtering, but starting with the example of characterizing the noise performance, so phase and amplitude noise performance of lasers. Well, what one would normally do is to beat the laser under test with the local oscillator, and detect that with the balanced photodetection, and then do some processing to re-extract the phase, so the time domain waveform representing the phase of the beat signal. Now, of course, this digitized signal contains the target noise that we want to measure, so relative intensity noise and frequency or phase noise, but also a lot of measurement noise, say from the photodetectors or the analog to digital converters. So this means that when our signal to noise ratio starts decreasing, so we have, say, a very weak power from the laser because it's a new device which is still not performing very well and so on, then we can see that the actual measurements that we get is very far from the real target noise that we want to measure. So the measurement noise effectively distorts our estimation, especially for low SNR measurements. So what we have been looking at then is to use Bayesian filtering to suppress such measurement noise. How can we do that? Well, we can do that because we have an idea of the statistics of our measurement noise that is affecting our data. And then we can use the Bayesian filtering framework based on Kalman filtering, where we use this probabilistic framework to estimate the sequence target, so the noise that we want to measure from, which is just from the laser, from the noisy observation, where noisy means affected by measurement noise. Now, as a brief cartoonish explanation on how unscented Kalman filtering works, what you see here is the example of a bouncing ball. So that's the blue crosses, and we are trying to get the trajectory of that ball from our noisy measurement, so the orange circle. And by applying Kalman filtering, we can see that we can decrease a lot the impact of the measurement noise, getting this gray estimate. So we can almost recover the true signal from the noisy measurements. And this is then applied to the characterization of a phase noise, so versus frequency of a laser. And what you see here is a number of, you have in black the curve extracted with conventional methods, so where we are strongly affected by the measurement noise, especially at high frequency. Well, the moment we start applying this Bayesian filtering approach, so the blue curve, you see that things are improved a lot. So we can get rid of this noise floor, which is a measurement noise floor, using the conventional method. And this blue curve fits quite well with state-of-the-art, very advanced measurements technique that are commercially available. So overall, we see that this Bayesian filtering is effective in removing the measurement noise and revealing the actual true laser noise. Now, other than applying this for a single laser, we can extend the framework to track the performance of frequency combs, so in terms of phase and frequency and intensity noise. And we can do that on a per line basis, which allows us also to get correlation matrices or covariance matrices, where we can correlate the noise performance amongst different lines of the frequency combs. And as frequency combs are very important, not only for potential communication application, but for spectroscopy and a lot of other very fundamental physics applications. Well, knowing very well the properties of our frequency comb is quite crucial. Now, the nice thing of being able to deal with measurement noise within this Bayesian filtering framework is that then what we can do is we can still track the phase noise at a very low level of SNR. And this is what you see in the next slide, as soon as my computer decides not to be stuck. Yes, sorry. That's what you see over here. So what you see is a number of curves where the important thing is, again, is phase of frequency noise as a function of the frequency, so frequency noise spectrum. And what you see over here is the black, cyan, and blue curves, which are the estimated noise performance of the laser for 3 different laser output powers. And you see which is corresponding then on signal to noise ratio on our measurement. And what you can see here is that when the laser power goes from -50 to -60 to -75 dBm, we are basically unable, we are dominated by the measurement noise, and we are really unable to see what are the inherent properties of the laser. However, if we apply this Bayesian filtering scheme, you see the 3 curves down here, they are pretty much on top of each other regardless of the SNR of our measurements, at least within some limits. So we can have measurements that works, or a method for extracting the phase and frequency noise from the measurements that works over a wide range of input power. And the fact that it works at such a low power as minus 75 dBm then led us to try to apply this for quantum phase estimation. So this is very important for quantum communication, especially continuous variable quantum communication, where the information is encoded on the phase of the single photons transmitted. And what we have done this here is trying to recover some phase that we ourselves imprint on a laser. Now this modulate or phase modulator laser is then attenuated to the single photon level. And then we are trying to track the phase after balanced detection. And what we see here is that the phase variance that we measure is very, very close to the quantum limit. And you see here that the numbers in terms of input power are extremely low, which means that the signal to noise ratio of our measurement is equally or is also very low. And overall, we see that we have a very negligible penalty compared to quantum limit. And this is, we think, is mainly due to the fact that this quantum limit needs to actually be estimated depending on the laser and local oscillator line width. So if we have a slight error on that line width estimation, which is sometimes very difficult to know with very precise accuracy, that might actually be the source of the penalty that we see, not really from our measurements. So just to conclude, machine learning or the machine learning toolbox in general can provide several advantages for applications in solving problems related to optics and photonics. So it's particularly effective for learning or inverting complex mapping, as well as filtering out statistically different noise sources. So overall, there's a lot of problems where we see that machine learning can help. And we do think that this is sort of a toolbox that needs to be known by electrical and photonics engineers, pretty much the same way as some of the basic math is. But in general, we see that there's a general lack of researchers that can bridge across the fields, so that can both understand machine learning and optics. So with this, I would like to thank you for your attention, acknowledge our funding agencies, reiterate a little bit on the fact that we are trying to solve ourselves or address ourselves the lack of researcher, and we have some PhD and postdoc position open in our group. And with this, I would like to thank you again, and I'll be happy to take questions.
Yeah, thank you, Dr. Francisco. That was really a very nice lecture. You just started with the introduction of ML for ML, then you went on how you can apply these for photonic applications, right from encoders, decoders, and then phase amplitude measurements. So it was really a very nice talk. Before we move on to take questions from the audience, our head of the department has also joined this meeting. So I welcome you, sir, and I request you to speak some words at this point.
Can you hear?
Yes, sir.
Yeah,
Yes.
my video is different.
Yeah.
And I'm very glad, sir, to see your talk, though a little bit late I joined. Francesco, sir, indeed, have good connection with this Danish, actually Aalborg University, and one another professor I know from IT department. I'm not getting. So he visited SRM also. So sometime back, and of course we have that Aalborg University, now Aarhus University. Indeed, I was in 2000. I was in Denmark. Some 2 years I was there in Aalborg. So not now, 20 years back. So indeed, that's what we were telling, that utilize the latest techniques available in photonics or some kind of thing, so that we can get a different dimension, this optics, fibers, and some other kind of thing, which will be the future technologies. So here also at SRM we started especially giving some importance to this photonics. Indeed, we are very glad that you are giving a webinar, and especially linking with ML, machine learning and deep learning. These techniques will rule the next coming years and everything. We are very glad and we are very fortunate that we got this webinar in this pandemic time also. Thank you so much for your sharing your knowledge with our students and faculty. Thank you so much.
Well, thank you for inviting me too. And well, then I hope that this might actually lead to some further collaboration also between you and DTU, not only Aalborg and Aarhus then.
Definitely, definitely, sure. Thank you.
Thank you.
Thank you, sir. So we'll have a small discussion. If anybody is interested in asking questions or any clarifications, you can unmute yourself and you can ask. Yes, OSA student members, other members, please, you can clarify your doubts. I think this is a very nice opportunity. Ma'am, you want to share something?
Yeah. Yes, I have a question.
Please.
You were discussing on fiber end-to-end communication. If there is a possibility of bringing in ML into it, then I think security aspects also we can bring in and program as such and then get things done.
Yeah, definitely application of machine learning within network security and networking in general. That there's a lot of focus on that. We don't go that far up, say in the layer stack. So we try to focus more on the physics and the physical layer. But I know like there's say a cousin university in Sweden, where they have a group that is very strong, working on application of machine learning for security and how to basically redirect traffic in case of network failure or in case of detection of eavesdropping and similar attacks. I don't know if that fully answers.
To start with, the ML toolbox available should be fine to start with.
Yes, absolutely. I mean, there's a lot of tools already available for similar application. At the end, for some security application, classification of a threat is always the first step. So applying pretty much the same approach as you would do for a spam filter is normally the clear direction.
Yeah. Thank you.
Yeah, I think Shamal sir is there. He is interested in having some discussion.
Please.
Thank you very much. It's very information oriented talk. I'm an experimentalist. I'm Dr. Shamal. I worked at Czech Republic, Prague, UFE, Institute of Photonics and Electronics. Yeah, so I worked with Dr. Pavel Honzatko in that group, nonlinear fiber optics group. And I'm basically interested in fiber optics, nonlinear optics, and terahertz application. So I'm an experimentalist, as I said. So what type of analysis that we can do and where we can start with these things means we have studied the laser stability and all these nonlinear effects, forward mixing in fiber lasers. So where we can start with means how to incorporate this in, because this is a very new field to us. Though we are doing the analytical calculations, numerical calculations through Jigma-Glandau equation, master mode locking equations, but how to use that? Do you can suggest some of the literature review or some books that the students can be helpful for that?
Well, so there's definitely a few review papers on application of machine learning in photonics. However, I think and this is maybe part of the challenge here. I don't think there's anything as close as, you know, a book about machine learning in photonics, unfortunately. So and that's a little bit the yeah, actually the challenge in sort of using the tools within photonics, because it sort of requires two different domain knowledge. However, I mean, I'm an experimentalist myself, believe it or not. So I think from at least my perspective, I mean, the one of the key interesting advantages of some of the tools from the machine learning toolbox is exactly that you can apply them directly onto you know, experimental data. So the example of the Raman amplifier, we started, of course, with testing things using the Raman solver or Raman modeling first, just to verify that things were running. But then we actually quite quickly went into trying to see whether our neural network-based model could actually learn the full system from experimental data. So that there's a lot of offline processing, but the most time-consuming part, I would say, is actually the data gathering in the lab. So that's I think one of the interesting aspects, and I think it's also maybe the real advantage of machine learning, because, well, if you are relying on numerical models already, or analytical, even better, then you don't really need a lot of machine learning. I mean, when you already have the models, well, then you should pretty much use those, unless maybe they are too slow, and okay, machine learning might still provide an advantage there. But the key challenge is when you go into you know, the experimental data where it's not easy to find a model that perfectly captures all the nuances and details from an experiment, say, for example, even including, you know, noise sources or fabrication imperfections, or well, if you are designing a fiber lasers, well, how well do you know splicing loss at every point, and so on, for your modeling. So I think really just having, to me, it's maybe more a matter of understanding what tools are available, and then once one has at least a general overview of the tools, then figuring out which one you can apply to your problem. And the thing is that the entrance barrier, I think, for machine learning as a field has actually lowered quite a bit over the past few years, because there are very effective tools for which no real, you know, deep knowledge needs to be present. So there's a lot of frameworks readily available, say, for neural networks and so on, in MATLAB or in Python. So there's frameworks developed by Google or by Facebook. And at the end, maybe at least from my perspective, I mean, some of the key problem in the core machine learning world are a lot more complicated than some of the problems that we are facing in photonics. So we don't need necessarily the state-of-the-art tools in their field. I mean, I think really the techniques that we are currently applying, they were probably developed, you know, 30 years back in the machine learning field. And they're still quite effective for photonics right now. So I think really some basic knowledge and understanding is already quite powerful.
Yeah, thank you. Thank you for your.
I hope that kind of answered your question. I mean, it was maybe not super precise, but
No, yeah, basically it is a very new field, and people are maybe uh, only last few years people are listening about the machine learning with optics. It's very nice to maybe start now because there are much thing we can do. I'm really interested to study the cascaded nonlinearity because it's the by cascading of 2 second order effects, you can trigger the third order effects. So, and there is no specific model now. So, I really want to work on that. That's why I asked. Thank you. Thank you very much.
yeah, thanks for the question.
Hello, sir.
Yes, please.
I'm Dhanlakshmi from same department, sir. Sir, we are working with fiber bag grating sensors. We are working for different applications. Sir, since there we are dealing with huge data, and now we started working, taking up machine learning for peak detection of the wavelength and the wavelength shift. Any idea of working with the experience and working in that thing, sir? Or you can throw some lights on that.
Yes, yes. No, thanks for this question. This is actually something that I haven't put on the slides, mainly because I'm not too involved in that project. But we do actually have a project exactly on that, to be honest. So on basically using fiber Bragg rating sensing and trying to enhance the resolution in terms of mainly temperature sensing. And there we have been applying a number of machine learning tools, especially with the Gaussian regression and mixed Gaussian statistics to try to enhance the basically the step or the temperature steps that we can resolve from the spectra measured from the sensors, so after the interrogator. Now I don't quite have the references in the slides, but I'm fairly sure you should be able, if you pretty much search for not myself because I'm not involved in that directly, but for my group leader's name, you should be able to find at least a couple of references which might be helpful and giving you some perspective there.
So very happy to hear this from you. So with your permission, can we contact you through mail?
Oh yeah, absolutely. Yes, I mean, I don't know if I should maybe go back to the
yes,
very
sir,
first
please,
slide.
Sir. Yeah, I will just note it, sir, please.
You have my email. Otherwise, Rohan is very welcome to share it around. Yes, so you got my email there. Yes, by all means. I mean, also further questions you might have afterwards. I mean, feel free to drop me a line. Be happy to discuss things offline as well.
Thanks, sir. Thanks a lot, sir. We got really very great inputs from your talk. It was quite interesting, sir. Thank you.
I'm happy to hear that.
Dr. Francisco, I have one question to ask.
Please.
Yeah, so in the last couple of slides, you were talking about the phase measurements. So
yes.
As we know that phase noise is one of the important characteristic in microwave photonics. So measuring phase noise is very tedious. Maybe you may have to go to theoretical calculation or from using some DSP or measuring it from the spectrum. So it always it's a bit troublesome if I'm not wrong. So can you just highlight something about that on how we can go for this phase noise measurement? I think there was some graph which you had showed.
Yeah, so let me just yeah, I mean, what we have been mainly focused on is just lasers and frequency combs, simply because that's that's the projects we have running and collaborations on that.
Okay.
But one key advantage actually that we see from using this framework, um,
Yeah.
yeah, you can see it over
Yes.
here,
Yes. Yeah.
where what it really helps is the high frequency part, which is probably something that also for microwave photonics is interesting, at least to my understanding. So I think if you use optics to generate oscillators as specific frequencies and so on, I think you can really apply the same techniques. I mean, I guess shaped frequency combs are something heavily used, at least to my understanding, in microwave photonics as well. So yes, I think similar techniques can definitely be beneficial there. Now we haven't done direct investigation in that direction yet, but yeah, the main advantage is being able to detect correctly the high frequency part of the phase noise spectrum, as well as perform measurements in very low SNR conditions.
Okay. So basically here you are trying to eliminate the noise as much as possible so that you'll be able to gauge what is the contribution of lasers noise in that, if I'm not wrong.
Yes, exactly. So I mean, what we really want to do is get rid of the contribution from our measurement setup.
Okay.
So the photodetector, the analog to digital converters, I mean, anything that is not the laser, we still need to measure both the laser and the local oscillator. So that's a little bit more tricky to differentiate because the two noises sources have similar statistics. So if they have similar statistics, then it's not that straightforward to filter them out. But if they do have a different statistics, then there's quite a lot that can be done to remove them.
Okay. Thank you for the answer. So any more questions from the audience?
Good afternoon, Professor Francesco. I am Dr. S. Satya and working in the same department. Actually, DTU is very famous for photonic crystal fiber fabrication, actually. So normally here, what we are doing is we are doing simulation, like designing of photonic crystal fiber using some either finite element method based simulation tool like COMSOL or EFTDD numerical. We are mainly depend on that. So the main problem here is it consumes a lot of memory to to design a single design, actually to design a single photonic crystal fiber design. So is there any scope on like a machine learning approach to get like faster as well as accurate results, like for example designing a photonic crystal fiber for supercontinuum generation application? So if you want to design, like we are varying two different parameters like diameter of the halos as well as pitch, and we need more specific, like we need more RAM capacity to run the simulation tools like COMSOL or numerical simulation tools. Is there any scope for for this machine learning tool to design these photonic devices photonic crystal fiber?
Yeah, thanks for the question. So, no, yeah, please finish.
Yeah, yes. Like this is my question.
Okay, good. Yes. So the first disclaimer is that I'm nowhere close to being an expert on photonic crystal fiber. However, maybe taking the question a little bit more general, there is work where I think published over the last year, if I remember correctly, where this inverse system design framework has been used to design optical fibers. I honestly cannot remember whether there were photonic crystal fibers. It might have been, but there were some specialty fiber. So with the target applications, so defining a certain dispersion profiles and so on. So this is maybe the first part of the answer. The other part regarding the memory, Well, it's a yes and no kind of answer. I mean, unfortunately, machine learning is not known for its low computational complexity. So we have a lot of challenges in terms of memory and computing power for machine learning. However, one thing that could potentially come to mind from the machine learning toolbox in terms of the design is that, well, if you want to vary only few parameters and, I mean, maybe restrict your space of possible outputs, what you can do is you can apply some methods where you try to it's basically this mainly unsupervised learning approaches that I briefly touched upon in the introduction, where you might want to just focus on the most important, so to extract the most important parameters from your model and try to link, you know, understand what parameter has the highest impact on the final outcome. And that way you might sort of simplify your model by removing the number of parameters if you figure out that some parameters are not particularly important. Now, I suspect that you probably have a reasonably good idea of that already. But I mean, maybe applying some principal component analysis, that's at least the main flavor of the method that I'm referring to, could be maybe beneficial.
Okay, thank you, Professor. So I will look into the similar kind of articles, like maybe like I will search. Thank you, sir.
Yeah, you're welcome. Thanks for the question.
Yeah, so I think there are no more questions from the audience.
1 second.
Yeah.
Is it audible?
Yes, ma'am.
Yeah, I am Dr. S. Kritika. Good afternoon, sir. Your topic is really an eye-opening. Sir, I just want to know some more information about training using the data sets. For example, you have explained about Raman amplifiers. Can you say like what characteristic is given as data set, or how many data sets, any for anything? Just some more additional information about training using the data sets. Any experiment, some more little bit.
Yes, that's a very important question, because training is always the most important aspect, and data selection as well. So of course, if you are sending the wrong, or you're using the wrong data set to train your model, that will have a significant impact on its performance. So maybe to focus on the simple example of the Raman amplifier. I mean, what we really use to train it is sets of, say, laser pump currents and the corresponding gain profiles. So what we do to build this data set is we really uniform sample the currents within, you know, the ranges that the pumps can operate at, and then for each sort of set of n currents, we apply the currents to the pump lasers, we measure the spectrum. Then next random set of currents, measure the spectrum. Next random set of currents, measure the spectrum. And then at the end, what we end up is with a few thousands measurements where each measurement corresponds to a set of n current values and m gain points, where m is the number of frequencies. And we use that for training our model. Now, the most important part is that the neural network are universal approximators, meaning that they can they're very good at interpolating a curve. However, they are very bad at extrapolating generally. So what you want to make sure of is that you always have the boundaries of your system, or of your interval included. So you might want to make sure that when you measure, you have a case where, you know, the pumps have the minimum and the pumps have the maximum, for example. So in your n-dimensional space, you need to cover the edges or the boundaries of your space in order to be sure that the training gets done in an effective way. Does that make somewhat sense? It wasn't a very general answer, but maybe the specific example helps in understanding how to build data set.
Thank you, sir. Thank you very much for your inputs.
You're most welcome.
Yeah. So I suppose there are no more questions. Okay. So thank you, Dr. Francisco, for your kind acceptance, and also you were very enthusiastic while planning this lecture also on knowing what about the background of the students and everything. So I'm thankful to you once again, and I request Pawan to propose the vote of thanks.
Well, thank you again for inviting.
Yeah, thank you. Pawan, are you there? Pawan. Yeah, start quickly. Pawan, you're not audible. Hello, Pawan.
You wind up, Rohan.
Yeah, okay.
Wait for some time if you one attempt, but you
I think there are some technical issues.
okay.
Yeah. So I once again thank you for your kind acceptance and taking time from your busy schedule and delivering this lecture on this very innovative topic. And I would like to thank the management of SRM and also our head of the department for their support. I also thank Shanti Prince ma'am, who is our chapter advisor, for her continuous support. And finally, I thank all the attendees, participants who have joined this lecture virtually from different parts of this country. So I once again thank each and everyone. Thank you, Dr. Francisco. Have a good day.
Yeah, thank you. You too.
Thank you.
And
Thank
again, you're very welcome to reach out to me at the email address
Sure.
and, for further discussion.
Sure.
Okay,
Sure.
thanks
Again
Thank
for
you.
the invitation and have a
Yeah.
great day.
Thank you.
Bye-bye.
Thank you very much.
Yeah. Bye. Ma'am, shall we end the meeting?
Yeah, you will.
Okay.